Greeting, my name is Afshin Alaghehband and today I will be presenting you our paper with the title Flying Base Station 3D Positioning Considering Path Loss, Coverage Area and QoS Constraint. Research and written by me, Mrs. Bangash, Dr. Mohajerzadeh and Dr. Vahedian. In this presentation, first we will talk about benefits and applications of flying base station, and then shed light on the challenges faced while using flying base station. Then we talk briefly about the main idea of this article, the state of the art, and then main goals and innovations. We will also discuss the system model and the numerical result obtained from the test. Let's first talk about the benefits of using flying base station. FBSs can provide better coverage and quality of service. FBSs don't need infrastructure, which means they can be quickly and cheaply provided. The inheritance property of FBSs provide high flexibility and 3D mobility. They can have line-of-sight communication which increase interference. Amongst the various applications of FBSs, they are particularly used in areas where there is no ground base station or where they have been destroyed, sometimes due to natural disaster. They can be used during events where they need to serve a lot of users, and it also have a wide application in IoT. The many applications of FBSs bring many challenges with itself, such difficulties in finding the optimal 3D placement and channel modeling, energy limitations, flight time constraints, providing the required data rate and QoS, and security and backhaul connectivity constraints. Now let's dive into the key ideas of this article. We deal with 4 different aspects in the article. The first one deals with optimizing the 3D locations of the several flying base stations using the set cover problem. Then we need to transfer the continuous space of the problem into the discrete space. After that, we need to apply weight in the set cover problem to optimize the energy consumptions of the transmissions. Lastly, we obtain the mean points required to serve the users under coverage area, QoS, and the path loss constraint. The set cover problem is a mathematical model which is normally used in math problem, and it is rarely analyzed in the field of computer. In the previous work, it is used to achieve the required reliability in wireless sensor network. Another work has used it to optimize the position of solar lamps in the actual farmland. Another have also used the set cover problem in the view planning problem in robotic active vision. Since the CP is an NP hard problem, these articles have used heuristic and linear optimization and also deep learning to solve the set cover problem. When it comes to drone positioning, many different aspects have been analyzed in the previous article, but the main properties considered are 3D positioning, service time, QoS, multi-drone trajectory, power consumptions, and etc. Frequently used methods to solve positioning problem in previous article include linear programming and learning-based algorithms. Other methods include artificial B-cloning and non-orthogonal multiple access problem are mentioned here. There are 3 main contributions in this article. Firstly, we present an innovative algorithms to convert the continuous 3D space into the discrete one. Secondly, we use WCP to find the optimal 3D position for FBSs under coverage area, path loss, and data rate constraints. Lastly, we optimize the transmission power by considering the weight in the set cover problem. To better understand the system model, let's take a look at the set cover problem. In the set cover problem, we are trying to find the universal set by union of the least number of subsets. And in the weighted set cover problem, we are trying to find the lowest sum of the weights. In our model, we follow 4 steps. First, we provide the selected position point and apply constraints on them. By this way, we will generate subset, and finally we find optimal FPS's position. Since FPSs can locate in any position, we cannot solve the problem with infinite points. Therefore, we provide a 3D mesh grid to discrete the 3D infinite space. To achieve this, we divide the lengths and widths by heights and select the heights from the set of heights. By this, we will have at least 2 points to cover each user in any point. This figure shows the resulting 3D mesh, which has different densities at each height. After finding the selected position point, we will reduce them by removing useless points. This is done to improve the problem solving time. The points which couldn't provide service to any user are considered useless. In this model, we have 3 constraints. Since we couldn't add constraints in the set cover problem, we will create a subset considering the constraints. To achieve this, we have a binary variable Sij, which is initially equal to 1. If any of the constraints fail, we will change it to 0. The first constraint is coverage area. If Dij, which shows distance between user and FPS, is greater than height radical 2, Sij is set to 0. The second constraint is pass loss, and to calculate that we need to find the probability of LOS and NLOS. After that, we calculate pass loss in both LOS and NLOS situation. Finally, we multiply the probability of each LOS and NLOS to the pass loss to get the final pass loss. The formula to find the PL max is shown in the slide, which is we use to find the probability of providing service to each user. If PLij is greater than PL max, Sij is set to 0. Lastly, we shed light on the data rate constraint, which states that each FPS can only provide service to a user if its remain data rate is greater than the data rate required by the user. If this constraint is not satisfied, Sij is set to 0. I must mention that user with the lowest probability of being served will be served first. Subsets are created based on the variable Sij. If Sij is equal to 1, user I will be in the set J. After creating subsets, we use WSCP model to find the optimal placement. Wk shows weight of each subset and is equal to height to minimize transmission power. In this problem, we are trying to minimize summation of product Wk and Xk. Xk is the binary decision variable which shows subset K is selected or not. Second condition shows every user must be served at least by 1 FPS. To evaluate our model, we consider sample scenario which the details of different variable is shown in the slide. This figure illustrates the number of required FPS to serve all users under different constraints. As you can see, pass loss constraint has the lowest effect on the problem. But on the other hand, we have coverage area and data rate constraint, which have the major impact on the problem, so much that together they can mask the effect of the pill. Keeping in mind that we cannot consider data rate constraints solo. To compare SCP and WSCP expect in PL constraint, in other cases WSCP needs more FPSs. However, in all cases WSCP can solve the problem with a lower cost. To compare our model with other algorithms, we use the result of experiment down in article cited 12. For this, we rerun our model in the environment introduced in the article 12. This figure shows the result of the comparison. As you can see, WSCP and SCP almost need half of number of FPSs to provide services to the user. In conclusion, the numerical results show the performance of the proposed algorithm based on the set cover problem. The 3D MPR has been presented to reduce the suggested selected point and generate the required subset of the WSCP. The data rate constraint is the most effective among the three mentioned constraints. Applying the effect of weight in the problem reduces the total transmission power of FPSs. Thank you. If you have a question, feel free to ask.